Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Rotate image, Leetcode 48. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an n-to-n 2D matrix representing an image, and we need to rotate this image by 90 degrees clockwise, and we have to rotate the image in place, which means we have to modify the input 2D matrix directly, and we shouldn't allocate another 2D matrix to do the rotation. Then in example 1, when we rotate the given matrix clockwise by 90 degree, the first row in input matrix becomes the last row in rotated output matrix, and the second row becomes the second last column, and finally the last row becomes the first column, and this is how this matrix is rotated. And similar is the case in example 2, where the first row transforms into last column and rest of the rows follow suit by taking their respective position in the rotated output matrix. Now there are many ways to solve this problem, and one of the simplest ways is to create a copy of the matrix as the rotated version. So to build this rotated copy, we can use two nested loops, one for rows and one for columns. Now we can see that first row in the input matrix moves to the last column in the rotated matrix. Second row moves to the second last column, and so on. So in other words, for a matrix with n rows and n columns, any cell in the ith row and jth column moves to the n-1 minus ith column or the ith column from the end in the copy matrix. For example, this 4 moves from the second row to the second last column in the output matrix. Additionally, the row for this copied cell is same as the original column. For example, here this 4 in second column moves to the second row in the output matrix. So in summary, we take an element at position I, j from the original matrix and set its value in rotated matrix at jth row and n-1 minus ith column. And we repeat this process for all elements, building the rotated matrix from the scratch. And once the rotated copy is built, we can copy it back to the original matrix, as we need to update the matrix in place. Now the time complexity of this approach is O of n square, since rotating the matrix into temporary copy requires O of n square iterations, since we visit all the elements in the matrix to compute the new position, and copying back the rotated matrix back to the original again takes O of n square time. Hence the overall time complexity will be O of n square, and the space complexity will also be O of n square, as we are using this temporary copy matrix to store the rotated version of the matrix. Now, even though this approach is simple and works, it requires extra space, which goes against the problem's constraint. Now let's see how we can solve this problem without using any extra space. First, let's explore a method we refer to as force swap technique, and you will soon see why it's called that. If you observe carefully, this matrix can be visualized as concentric layers. So this is the outermost layer, and this is the inner layer, and so on. And suppose we are processing the outer layer, then each element in the top row of the current layer is moved to the right column of that layer. Similarly, the right column's element is moved to the bottom row, and the bottom row's element are moved to the left column, and the left column's element is moved back to the top layer. And same is true for any given layer, like inner layer. Now, we begin from the outermost layer and move inward, processing each layer, and each layer is like a square ring. So number of layers that we have to process is n by 2, since we have n rows and n columns, and square has two sides for each layer corresponding to rows and two sides corresponding to column. Hence, the total number of layers that we have to process is n by 2. For example, here number of layers are 2. Now for each layer, we perform force swaps to rotate the elements to respective layers. For example, this 5 moves to this position in the output matrix, 11 moves to here, 16 moves to here, and 15 moves to the position of 5. And since we are performing these force swaps, before overriding this value, we should take the backup of these elements in the temporary variable. For example, before replacing this 11 with 5, we should store it in some temp variable and then use it to propagate the value to this cell. And we should repeat this process for every element being swept. And once we have processed this element, we will process next element, shifting it to this cell. Then 10 moves to this position, 12 moves to this position, and 13 moves to position of 1. And we continue this process for all the elements within the layer. And this brings us to an important point, which is how many elements are processed in each layer. Here, for example, for the outermost layer, we need to process 3 elements, which are 5, 1 and 9. So we start from cell 0, 0 and go up till the second last element in the row, as the last element is already swapped with the first element in this row during the rotation process. And the same logic applies to other sides of the layer. And generally speaking, the iteration starts from the first item in the row based on the layer. For instance, in the outermost layer or layer 0, we start with the element 0, 0, and for layer 1, we start from cell 1, 1 and so on. Similarly, the last element in the row in a given layer is always at the last column of the current layer, which can be expressed as n minus layer minus 2. For example, for the outermost layer, it is this element, and for the inner layer, it is this element, and so on. This calculation works for the top row, and as we process the top row, we automatically enforce swaps for other 3 sides of the square ring. Thus, iterating over the top row is sufficient to handle the entire layer. Now, when we perform the swaps, we need to first take a backup of the element that still needs to be propagated. For example, we take backup of 11 before 5 replaces it, so that 11 can later be propagated to replace 16. However, a better approach is to take the backup of just one element, say the top element, which is 5 here. So now we can use 15 to replace 5 at the top position. And now since the value of 15 is already used, we update its position with 16 from the left column. And then since 16 is already used, 11 replaces 16. And finally, the backed up value of 5 is used to replace 11 in the right column. And we are done with the 4 swaps for that element. Now let's see how we can programmatically get the positions of the top, right, bottom and left elements for swaps within the current layer. Let's say we iterate over the layers with the variable called layer, which represents the current concentric square being processed starting from the outermost or 0th layer, and I be the iterator within the top row of that layer, moving from left to right, processing one element at a time, that is, swapping it with elements on the other side. So now let's focus on deriving the positions of these elements within the current layer. For the top row element, the row is fixed, which is given by the layer itself, but the column changes with the index I, moving from left to right. Similarly, for the bottom element, the row is again fixed, which comes from n minus layer minus 1, and the column changes in reverse from right to left, which we can get by n minus 1 minus I. Then for the right elements, the column is fixed, which we can get from the layer, which is n minus 1 minus layer, which is the right boundary of the layer, and the row changes with index I, where we go from top to bottom. And similarly for the elements in the left column also, the column is fixed, which we get from the layer itself, and the row changes in reverse, that is from bottom to top, which is given by n minus 1 minus I. And once we identify the positions of the cells, we can simply swap left to top, bottom to left, right to bottom, and top to right. And these swaps continue until all elements in the current layer are processed, and the process then moves inward to the next layer and so on until all layers of the matrix are rotated. Now the time complexity of this approach is O of n square, as each element in the matrix is visited only once, and the space complexity will be O of 1, as no extra memory is used. And now the question is, can we do better? And the answer is yes, in terms of simplicity. While the 4 swap method works efficiently, it can be challenging to write code correctly and handle edge cases in an actual interview setting. So let's simplify the approach a bit. For that, we can look at the transpose matrix to guide us. Transposing a matrix involves converting its rows into columns. For example, when we transpose this matrix, we get following matrix: where the first row becomes the first column of the transpose matrix and the second row becomes the second column in the transpose matrix, and so on. And notice how close the transpose matrix is to the output matrix. Here the first column of the transpose matrix is the last column in the rotated matrix. Similarly, the second column is the second last column in the rotated matrix, and so on. So this leads us to the simplified idea where we should first transpose the matrix and then we should reverse each row in the transpose matrix and it becomes a rotated matrix. And now let's see how we can transpose the matrix. We can transpose the matrix by swapping elements above the diagonal with the elements below the diagonal. So we can swap this 2 with 1, this 13 with 9, this 3 with 8, and this 15 with 11, and so on for all the other elements above the diagonals are swapped with the elements below it. And once these swaps are performed, the matrix is transposed. And programmatically speaking, we run two nested loops, I for rows and j for columns. And we only process the elements above the diagonal, that is, j is greater than I. Because for any element at cell I, j above the diagonal, we can get its corresponding element below the diagonal at cell j, I. So for each valid pair of indices, we swap the value at cell I, j with cell j, I, and this converts rows into columns and results in the matrix being transposed. And once we have this transpose matrix, we can just reverse the rows. So for example, first row becomes 15, 13, 2 and 5. And similarly, we will reverse the other rows as well to get this output matrix. And again, programmatically speaking, we loop through the matrix rows using an iterator I. And for each row, we iterate on its elements using the iterator j, going up to the center of the row. And during the iteration, we swap the element at the jth column from the start with the element at the jth column from the end. And this is how we reverse all the rows. Now the time complexity of this approach is O of n square, because transposing the matrix and reversing each row both take O of n square time. So the overall time complexity will be O of n square and the space complexity will be O of 1 because we are performing this operation in place. And even though this approach involves two passes, one for transposing and one for reversing rows, it is still preferred because of its simplicity and clarity. It avoids the complexity of managing swaps for multiple elements and edge cases, making it a reliable solution in interview settings. In today's video, I shared Python snippets to save screen space, but the equivalent Java code is also provided in the code link available in the description below. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.